Some students have requested some detail about hex and binary. First thing, we should know that everything on a computer is just a sequence of ones and zero, and we've got the human readable version of that, which is hexadecimal. It's not stored in hexadecimal in a computer. It just makes it easier to understand for humans. For example, binary, if we had 15, so we add up all the column heading, that's 15. In hex, that's just F. Binary, denary, hex. Now, some students have asked about shift. So if we had 4, if we left shift it once, it times it by 2. Everything gets shifted to the left, and it is again shift 2 equals 16. So left shift equals double, double, double. If we have right shift, so currently it's 6, right shift divided by 2 equals 3, and right shift again, we lose a bit because there's no decimal places in binary. Data loss, the remainder was lost. Odd number divided by 2 is cut off, so the 1 disappeared, and if we right shift again, becomes 0. What we must also understand, if we have only 8 bits stored and we left shift again, we actually lose a character. It is an overflow error, similar to adding 2 binary numbers together. We left shift to the left, it will cut off 1, and as you can see, 252, the number's actually going smaller instead of doubling because we have lost the 128 left shift by 1. We lose that 1 because there is only space for 8. That's only if they say it's 8-bit number. 128 left shift becomes 0. We've had an overflow error and the number has cut off. That's only if we have a space for 8 bits. Images. So digital images are made out of a grid of pixels. If you look here, it's got 8 across, 8 down. That's 16 bits in total. Each one is 1 bit, 1 color. So if we increase the width, for example, now it is 12 bits across, 12 times 8, 96 bits, times divided by 8 will be 12 bytes. Yeah, there's 8 bits in a byte. Okay, so when we have to do a file calculation, we do the width times height times the color depth. So if we increase the color depth, the file size increases. Now there's, for each, let's reduce it to 4 by 4 and 2 bits. 4 times 4 times 2 equals 32 bits. Divided by 8 equals 4 bytes. That's how you do the file size calculation. So remember, the more bit depth you have, more colors you can have, and the larger the file size. Less bit depth you have, smaller the file size, less colors you can have. Same with width and height. We times them together, so more width, more pixels, times them together. 16 times 16 equals 256 bits, divided by 8 equals 32 bytes. And then we can increase the bit depth, and 4-bit depth or 2-bit depth allows for 4 colors, equals 16 times 16 times 2 equals 512 bits, divided by 8, 64 bytes. Sound, we record the amplitude of the sound at regular intervals, and we take samples of the amplitude. The more sample we have, 20 hertz, 20,000 samples a second, the larger the file size, better accuracy to this original quality. And bit depth is how many bits we take per sample. The larger the bit depth, the larger the file size. And the calculation is similar. So for example, sample rate of 4, That's 4 samples per second. And bit depth of 4 times 4. And the duration is 10 seconds. So it's times 10 equals 160 bits divided by 8 equals 20 bytes. Increase the duration. Let's double the durations. Now it's 4 times 4 times 20. 320 bits divided by 8, 40 bytes. And that's samples. Sound. So we sample at regular intervals. And if you increase the interval, so there's a larger gap between samples, there's less samples per second, 2 samples a second, times the bit depth, let's say 2 bit depth, 2 times 2, 20 seconds long equals 80 bits divided by 8 equals 10 bytes. Let's look at some exam questions. Sound sampling. Question. Describe the process of sampling an analog sound wave so it can be stored in a computer. Let's mark this. This got 0 marks. The computer measures the sound wave at different points to see how loud it is. It then records these measurements as binary numbers so they can be saved. Now, that achieved no marks. It says different points. How loud it is, a non-technical term, too vague. Marking requires technical terms like amplitude and intervals. Let's look at a perfect answer. The amplitude of the analog wave is measured, so amplitude, yeah, and regular intervals, another mark. The measurements are then converted into binary form, so it can be stored. That's the third mark. Binary shifts. 8-bit binary number 010 101 is shifted 2 places to the left, so everything gets moved to the left. Remember, it's an 8-bit number. Identify the result and explain the effect on the number. The result is they've added more binary digits, 1 2 3 4 5 6 7 8 9 10. So it's no longer 8-bit binary. The number has become much bigger because we added 2 zeros at the end. It added 2 zeros here. Technically, if we didn't say 8-bit number, it just said it had a binary number, that would be correct. But because it says it's specifically an 8-bit number, which is normally the case in J277, we should stick to 8 bits and not go over that. So this is why the student got incorrect. Incorrect result, 8-bit registers cannot expand to 10 bits. Much bigger is too vague. Let's look at the perfect students. The result is 0 1 0 1 0 and 0 0. Shifting a binary 2 places to the left is equivalent to multiplying the original number by 2 to the power of 2. Correct binary result, it cut off the 2 numbers on the left. Identifies multiplication, correct factor 4. So if this is a 4 marker, you would have also said there was an overflow error, and you would have got an extra mark for that as well. Image metadata. Explain the purpose of metadata in an image file. Provide 2 example data that it might contain. Metadata is used to store extra information about the image. 1 mark the student got, like where it was taken or the time. That's extra 1 mark. This helps the computer organize the photo. Provide 2 valid examples, but fails to define the purpose. Data about data to allow correct rendering. Let's look at the perfect answer. Metadata is data about data, technical terminology there. Its purpose is to provide the computer with information needed to correctly display or render the image, such as dimensions. Examples include the image width and height. It's much better answer here. Includes a better explanation. We need the dimensions to show the image. And metadata is data about data, extra information inside an image. Let's look at this one. Explain how increasing the color depth affects the file size and quality of an image. 0 marks here. Increasing the color depth makes the image look better because there are more bits. It also makes the file larger. Looks better and larger are too vague. Use technical terms like range of colors, bits per pixel. Perfect answer. Let's have a look. Increasing the color depth means there are more bits available for each pixel, allowing for a greater range of colors. More colors, more bits per available per pixel to be represented, improving quality. However, since each pixel has more bits, the overall file size will increase. Explains quality. range of colors, and file size bits per pixel, 2 marks. So look at this one. Describe how increasing the sample rate affects the quality file size of sound recording. If you increase the sample rate, the sound is much clearer and more like the original. The file gets heavier to store. Clearer and heavier are not technical. Use accuracy to analog wave and number of samples stored. Let's look at the perfect answer. Increasing the sample rate means the amplitude is measured more frequently, more times per second. Amplitude is measured more frequently is a better answer. This results in a more accurate representation of the original analog wave, better quality, but increases the file size as more data points are stored. Explains quality, accurate representation, 1 mark, and file size, more data points. So you need to be the way to get marks in all of these questions is using technical words. Don't be vague and remember the points. Sound, remember sample, binary shifts, overflow, remember that. Remember that how to work out X. I've done another video of converting numbers. Check the channel. Images, width times height times color depth. The larger each one is, the larger file size. Remember, from bits to convert it to bytes, you're going to divide it by 8. Sound, it's all about sample rate, bit depth, duration. Again, divided by 8 to bytes. And that should cover this topic. One last thing actually, in the specification it talks about the least significant bit and the most significant bit, meaning the leftmost value that you're using has the highest value, 128, and the least significant bit, the number right at the start, has the lowest value. So this would be considered the least significant value on far right. And if we're using 4 bits, this would be the most significant bit. It has the highest value. I just want to, if it mentions what the least significant bit is or the most significant bit, just remember the leftmost bit is the most significant and the rightmost bit is the least significant, as it has the smallest value. For example, this only has 1, and all the way up to here that equals 228. So I think that covers everything here. And again, converting between binary and hex and denary, there's other videos already made for that if you want to check them out.